Greetings, everybody, and today we are going to discuss capabilities. Capabilities are an idea that I came up with, which I probably wasn't the first to do so, but capabilities work a lot like interfaces, which you might be used to in programming languages like C Sharp and Java. There is one difference, though, and it's actually a pretty big difference, even though it looks pretty small. And it's that one difference that makes capabilities absolutely awesome. So, before we start getting into the code here, let's discuss the traditional interfaces versus our new capabilities that we'll be designing here. So, to do that, we'll go ahead and have a look at this nice little slide that I worked pretty hard on. Pretty happy with it. So, on the left side here, we have our traditional interface, and so first we'll talk about that. Now, the point of an interface is to define a common way for objects to communicate. So, for instance, if I have uh, a huge selection of different types, but all those types have an action, then I can define an interface that says, hey, do action or something, and then make all of my types uh, implement that interface. And so now I can have, like, say, a list of that particular interface, and I can add all the objects that I want, so long as those objects implement that particular interface. So I can have a type A, a type B, a type C, all these different types. As long as they have that interface, I can throw them into that list and I can call their action. So that's essentially how an interface works. But here's the thing is there is that binding. I have to declare right here that this concrete object implements this interface. And as you can see in the example here where we have a foo and a bar, both these classes, they both inherit it. Well, in C++ it would be inherit, but effectively implement the ifoo interface. And you don't see ifoo here, but essentially ifoo has an abstract a pure virtual function called action. And this foo right here is providing an implementation for that action, and this bar class is providing an implementation for that action as well. So in these cases, I can spin up. See, basically, I'm saying I want an ifoo star. So this is the interface, but I'm creating a foo implementation, and here I'm doing another ifoo star. But this will be a bar implementation, and then when I call foo's action, I have it print foo, and when I call bar's action, it will end up printing bar. So that's essentially a quick and dirty rundown of how interfaces work. They're incredibly useful, but they do have that one caveat where there is this binding between the concrete object and the interface. That can get in your way in a few instances. One particular thing would be if you are using a third party which has classes that work very similarly to the interfaces that you're using. Specifically, they would have identical signatures. You can't just use those with your interface. You actually end up having to create an adapter because there's no way that the third party library knows about your interface, and therefore it cannot implement that interface. So yeah, you have to create an adapter in order to essentially forward the calls from that class to the interface essentially. So you end up with an extra class that all it does is bind and forward, and that's all it's doing. So it adds complexity. So in contrast, the capability system seeks to eliminate that binding. And in so doing, we decouple our code a little bit more, which is really nice. And we focus more on type signatures as opposed to inheritance hierarchies. And to me, I think that's a way better way to program because you can keep your classes down and eliminate dependencies a lot more. Because as you can see, that arrow is gone, and this class over here does not have a public ifoo or any other thing. This class has no inheritance hierarchy whatsoever. Likewise, our bar also has no inheritance hierarchy, and therefore neither foo nor bar are related to each other. These are two completely distinct classes. If I tried to assign a foo to a bar or vice versa, I would get a compile time error. So foo and bar have no dependencies on each other at all whatsoever. They're completely isolated classes. That's what we strive for, at least what I strive for when I program, is trying to keep that level of separation so I don't end up with unexpected interference. So we're off to a good start here. So now, how does the capability system work? Well, inside of our void do something here, we simply construct a fooable, and we'll call it foo. And in this case, all we're doing is assigning it a new foo. And in this other part, we have fooable bar. We give it a new bar. And then once I call foo.action and bar.action, I get the proper corresponding actions called. And how we're doing that is through runtime binding, where essentially we're essentially taking the functions that are inside of a foo and a bar, and we're holding on to it inside of our fooable, and then doing the call forwarding through the fooable object itself. So if that seems really complicated, don't worry about it. We're about to run through it. Turns out it's actually really simple to do, and thanks to C++11, it is very possible with C++ now. So let's go ahead and have a peek at that and see how to get started. All right, so we're back in our code here. It appears I have eaten my function main inadvertently, so let's put that back. All right, now inside my include here, include folder, I'm going to go ahead and create a new item. And let's create a capability that updates. Effectively, we don't care what it's wrapping. We just know that we want to call its update routine. And we'll just say its update routine doesn't return anything and doesn't take anything. Now, you can do whatever you want. You can call it whatever you want. It can return values. It can take any number of arguments of all sorts of different types. It doesn't really matter. But for this, we're going to keep it simple. So we're going to call this an updatable. All right, so how we do this is first, we're going to end up doing the bindings through the function class. And in order to do that, we need to include a function, or the functional names, header file. Sorry, having difficulty talking. All right, so now we're going to create a class, and we're going to call it updatable. There we go. Spell it right. And now we want to create our update binding. So we're going to do a std function. And now we pass in our signature, and it's going to be void, and we're not going to take anything, so I'm going to do void void. That second void is not required. And we're going to call it update. So there we go. Right out the door, we now have a functional updatable, or a compilable, I should say, updatable system. So if I were to go into main right here and include updatable.h, did I spell that wrong? Oh, I put an E in it. Okay, I'm not really sure how to spell that, but we'll go with that. Yeah, let's keep it consistent here. Okay, so if we create an updatable, and we'll call it A, all this code so far will compile. So if I hit Control-Shift-B, there we go, compiles great. And if I run it, it should also work fine. Yep, so no errors yet. We're not seeing anything, but we haven't caused any critical errors. But now if I do a.update, like so. Oops, okay, forgot to make this public. Come on. All right, whoops. Now we have an error. And the reason why is because we haven't provided an implementation yet. This update points to nothing, so it's going to explode violently, as you saw. So the first thing we should probably do whenever instantiating an updatable is we should probably provide some form of an implementation for its update method. And this is something that I actually for the longest time didn't know you could do. I don't know if this is new to C++11 or if it's been around a lot longer, but what we're going to do is we are going to create a templated constructor, which I think is just awesome. So we'll do updatable, and we are going to take a t ampersand, and we're going to call it obj. And now inside of our, oh gosh, I can't remember what that's called. Constructor list, initializer list. I think it's, whatever. Inside this thing, we're going to assign update to a lambda, which will be obj ampersand. And we are simply going to call obj.update, like so. And then we provide our constructor definition there. Don't forget that. All right, so now if we try to compile, we get a syntax error because there is no default constructor for updatable anymore. We got rid of it. So now it wants something that it can actually call for updating. So to do that, let's go ahead and create some types that we can play with. So we'll create an obj_a, and we're simply going to have void update. And we've already included IOStream. I did that before the video started, so if you haven't done included IOStream, go ahead and do that. So we're going to do obj_a updated. And let's go ahead and copy this and paste it. Create an obj_b. And we'll say obj_b updated. So now let's do two updatables. We'll do an updatable, actually let's do this. Let's do obj_a and obj_b. And then we'll do updatable ua, we'll take an a, and we'll do updatable ub, we'll take a b. So I'm going to go ahead and call u.a or ua again, because that's our updatable. In fact, you know what, let's spell these out. So updatable, let's do updatable 1 and updatable 2. All right. So now if we do updatable 1, we can hit dot and our update shows up. And we can do the same thing for our second one. So what should happen now is once this gets called, it should say obj_a updated. And when this one gets called, obj_b should be printed. So let's go ahead and see what happens. Oh, we got a syntax error. We always have a syntax error. I always get that mixed up for some reason. Okay. All right, so it compiled. So let's go ahead and run it. And there we go. obj_a was updated and obj_b was updated. So awesome. It looks like we just did an inheritance thing there, didn't it? Because we have an updatable and we assigned an a to it, and we have an updatable that we assigned a b to effectively. But as you can see, there is no inheritance hierarchy whatsoever between these two. These are distinct objects, and you just witness the compiler figuring it out and getting it right anyway. Now, the other cool thing about these is you can throw stuff into lists and all sorts of fun container objects. So what we could have also done is done a std vector of updatable, and we'll call this updater. All right, we'll have our obj_a and our obj_b. And what we'll do instead is we will do updater.pushback, and we'll pass our a, updater.pushback, do our b, and then we will use our handy dandy, auto, and handy dandy, what is it, ranged iterator or something? I can't remember. I am so out of whack right now. I apologize for that. I used to know all the names for these. I'm like out of it today. Horrible day to start up doing videos, but here we go. So, all right, we're going to have our updatable, or what do we want to call this? We'll just call it u. Why not? And we'll have our updater. And now we should be able to call u.update like so. And there we go. Compiles beautifully, runs beautifully. And we can keep adding as many as we want. So we can add b a couple more times. Then we can throw another a on here, a couple a's, finally another b. We run that. And there we go. So we have the A's updating, followed by some B's, followed by a couple more A's, and then finally another B. So yeah, effectively, our capability system allows us to do exactly what we set out to do. These are heterogeneous types. This is a heterogeneous container, well, more or less. All this container cares about is that there is an update inside of whatever classes we send to it, thanks to our wonderful updatable. This actually really kind of is our adapter, but it does it implicitly, so we don't have to. So if I start adding new types, such as a C, let's do this faster. There. And now I can throw that on here with a C. I can, of course, go ahead and add that to the list, compile, run, and, whoops, it works. And again, as you can see, there was no adapter pattern that was actually, we didn't have to generate an adapter for C. It just fit because this function signature works. So that is the true power of the capability system. This is almost as far as I'm going to take it. I'm actually going to do one more thing. And that is, you may have seen, if I go back to our slides here, that, the astute may have noticed I had some memory leaks going on here, didn't I? So what was actually happening was I created these iFoos and these fooables, and I assigned them to new instances of foos and vars. And of course, at no point did I call delete, so these actually leaked memory. So what I want to do is actually create a capability called a deletable. And the deletable will allow me to create a container of deletables and put all sorts of different objects inside of it that are pointers. And in so doing, we will have an RAII capable container that will delete any type under the sun as long as it has a pointer to it. That is some amazing power right there. So let's go ahead and get back into our capabilities over here. We'll create a new item. We will call this guy deletable. All right. Oops. We're going to include functional once again. Then we are going to create our class deletable. Go in publicly here. And actually, you know what? We do want to do that, but we also want a private section for this one because we don't want somebody accidentally calling the delete function, or the destroy function is what we're going to call it. So we're going to create a std function of void again, and we're going to call this destroy. All right, so the idea here is quite simple. The deletable is going to own whatever pointer it is given. And when the deletable itself goes out of scope, it's going to call this destroy method, which will be responsible for destroying the object in question. So once again, we'll go ahead and create our templated constructor. And we're going to take, in this case, a T star, because we need to make sure that it's an unowned reference to something, because we're about to own it. All right, so our destroy is then going to, take an item, or take our item, and we're simply going to call delete inside of our Lambda routine right here. And that's basically it, except for we need the destructor as well. So we're going to do deletable, and we're simply going to call destroy. And that essentially does it. So effectively what will happen is we can create lists of objects that we want to manage. And we can go ahead and do that here. I'm going to go ahead and delete this. Let's see. Let's do include. Yeah, we can keep it, I guess. Do deletable.h. And then we will do std vector deletable. There we go. Deletables. Now, keep in mind I will be omitting a piece of code, and pay very attention to the output once I'm done with this, because we're not actually going to explicitly delete this container. We're going to let RAII take care of that for us. So what we'll do is we're going to do deletable.pushback, and we're going to do a new object A. In fact, you know what? I'm going to go ahead and I'm not going to delete this, but now I'll delete it. We don't really need it. And sorry, for some reason my color scripting makes new really hard to see, but that's new right there. So let's go ahead and create a bunch of these guys. So we'll have A, B, B, C, A. That's good. All right, we don't actually care to do anything with updates anymore, so we should be able to do this. Yep, that works. All right, so if I run, whoops, something blew. I know exactly what happened. Okay, we're not done yet. We actually have a bit more work to do. So what we also need to do, because one of the issues we have is we actually have copy constructability going on here, and that's going to cause problems. So first thing we need to do is we need to turn that off. So, whoops, that's a const deletable, and we're going to say, yeah, don't do that anymore. And if we're going to do that, we also need to shut off our ability to use the assignment operator to copy a deletable. So if we run this, now we have an attempted to reference a deleted function, and you're going to get all this. Oh, it's so messy. This is one of the problems with C++ in its current state. I'm hoping future revisions are going to deal with that. Here's hoping C++ 17 corrects that. I happen to know what's wrong, but you're going to be, having a lot of fun trying to dig through all that to figure out what's actually going on. The problem is, since we don't have copy assignment anymore and we don't have copy construction anymore, it's getting confused. It has no way of knowing how to get one deletable to another deletable. And the reality is we need to be moving them. So what we'll do is we're going to create a move constructor. And we'll just call this RHS. And what we'll do is call destroy. And we're going to pass in RHS's destroy. Let's see. I feel like something's not quite right here. Let's keep going. All right. And we're going to set the RHS destroy to, oh, that's what I did wrong. There we go. All right. So we're basically going to set it to an empty lambda at this point. So effectively what that's going to do is when the RHS goes out of scope, it's going to call this lambda, which does absolutely nothing. And so it will just safely die and it won't attempt to actually deallocate the memory. Remember, with a move constructor, what's happening is we're taking this RHS value, we're taking its contents, and we're moving into our new instance. So the right-hand side here, it's going to be invalidated when we're all done. We've stolen its guts. It has no guts to do anything with. So we need to make absolutely certain that we basically debeak it or detooth it so it doesn't accidentally delete our data prematurely, and then once we delete it the second time, it would cause heap corruption. So yeah, that's why we're doing this right here, is to make sure that it just does a benign operation rather than corrupting our heap. So, all right, now if we hit Control-Shift-B, we have a successful compilation here. So, all right, so now if we run this, nothing happens. But we also didn't get heap corruption, so that's a big thing. So in order to see what happens here, obviously we might want to see the destructors fire off. So let's go ahead and do go ahead and create some destructor calls here. All right, do the same for these guys. This will be B. We need to make sure this says B, make sure this says C, make sure this says C. All right, now when we run this, ta-da! All of our objects were managed for us. They've all been destroyed. Everything is perfectly safe. And it's because our vector went out of scope. Our vector's destructor will automatically go through and destruct all of its elements inside of it. And since our elements are deletables, technically, that forwards the call off to the destroy method, which we assigned to the constructor, and thus deletes the item. So at this point, we've effectively made a safe way of handling heap allocations and making sure that once the scope ends, those heap allocations also get cleaned up. So that's pretty powerful. And in the next video, which I'll hopefully get around to doing shortly, I'm going to try to put all of this together. If you didn't see my video on type tokens, check that out before you check out the next video, because the type token system will be being reintroduced again. I'm keeping everything in the same project. That would be typer over here. But yeah, our next function is going to put all this stuff together and create, well, I'll go ahead and spill the beans on it. We're going to create a handy dandy factory system, which will allow us to create any type. It will manage that type. Once the factory goes out of scope, it will clean up all of its objects. And as the icing on the cake, it'll also allow you to iterate through all the objects inside of there by that type. So for instance, if I have object A's in there, I will actually be able to tell the factory, hey, I want you to call this function for every single object A, and it'll pass it that, each instance to that function and allow me to do some sort of manipulation on an object A, and it will be an object A. It's not going to be some proxy type. I will actually get a reference to an object A back, and in the same way, it would be if I pass an object B or an object C or an int or a float or whatever, I will get exactly that type back during iteration. It's a really cool class. I'm planning on using it for my game engine that I've got going, and it's surprisingly, once you have capabilities in place and the type token system in place, creating the factory is really simple, believe it or not. There's not a whole lot of code to it. I want to say, let me see if I have it here. I've got some notes on the side here. Yes, it will actually be writable in under 50 lines of code, and that is everything, including the iterator. So that's pretty impressive. So stay tuned for that, and hopefully I'll have that up within a day or so. We'll see what happens. Hope you guys enjoyed the videos. I know I'm still a little rusty. I don't know why, but for some reason I'm just having the worst time getting into these videos, so I do apologize for that. I've dropped terminology and made some mistakes. If you noticed anything glaring, let me know in comments. If you have any questions, let me know in comments. I will do my best to respond to them as soon as possible. And thanks for watching, guys, and I hope you guys make some awesome stuff with everything you've learned. Until next time.